Welcome to the Sleepy Astronomer, where we drift through the cosmos, one soothing mystery at a time. Tonight, we explore one of the most intriguing puzzles in the universe, dark matter, the invisible substance that holds galaxies together, yet slips quietly through our fingers. Before we begin, take a deep breath, settle in, and let your mind float among the stars. Where in the world are you watching from tonight? Let us know in the comments. We love knowing which corner of the Earth our fellow stargazers call home. Now, dim the lights, get comfortable, and let's begin our journey through the unseen. Dark matter. It's one of those phrases you may have heard whispered in science documentaries or late-night conversations under starry skies. A name that carries mystery, yet doesn't reveal much on its own. It sounds poetic, even a little haunting, and in many ways, it is. Because unlike stars, planets, or even clouds of cosmic dust, dark matter doesn't shine. It doesn't glow. It doesn't reflect light. In fact, it doesn't seem to interact with light at all. And yet, it appears to be everywhere. To begin understanding what dark matter truly is, or rather what it might be, we must take a gentle step back into the quiet realm of cosmic observations. For centuries, astronomers observed the heavens, tracking the movements of planets and stars, trying to decode the structure of the universe. And for the most part, the laws of motion and gravity helped everything make sense. Planets orbited the sun, moons orbited planets, and stars danced in spirals around the centres of their galaxies. It was orderly, predictable, comforting. But then, a strange whisper echoed through the data, a whisper that something wasn't adding up. Imagine you're watching a carousel spin in the dark. If you could only see the horses, and not the poles holding them or the structure beneath, you'd expect the horses closer to the centre to move faster than the ones near the edge, just like cars on a roundabout. That's what Newtonian physics would predict. But when astronomers like Vera Rubin began measuring how stars moved in galaxies, they noticed something astonishing. The stars on the outer edges of galaxies were moving just as fast as the ones near the centre, sometimes even faster. That shouldn't happen. The visible mass of a galaxy, all the stars, planets, gas and dust, just isn't enough to create the gravity needed to keep those outer stars from flying off into space. It was as if something unseen was surrounding the galaxies, like a massive, invisible halo of gravity gently holding everything together. This invisible something began to take shape in the scientific imagination. It wasn't made of ordinary atoms like we are. It didn't glow or absorb light, but its gravitational pull was undeniable. And so, astronomers gave it a name, dark matter. Dark because it's invisible, and matter because it behaves like a substance with mass. The idea of dark matter wasn't born out of fantasy or science fiction, but out of necessity. The universe simply wasn't behaving as it should if we only counted what we could see. And the more we looked, the more signs of dark matter appeared. In massive galaxy clusters, giant gatherings of galaxies held together by gravity, scientists noticed that the galaxies were moving too quickly to be held together by the gravity from visible matter alone. There had to be something more, something hidden, something powerful, something dark. Gravitational lensing offered yet another clue. This phenomenon, predicted by Einstein, occurs when a massive object bends the light from something behind it, like a cosmic magnifying glass. When we observed lensing in the universe, the amount of bending suggested there was far more mass in these systems than what we could actually see. Again, dark matter silently revealed itself, not by shining, but by shaping. And so, piece by piece, a quiet puzzle began to form. Astronomers and physicists in labs and observatories around the world began working to understand this ghostly presence. It was as if the universe had a hidden scaffolding, an invisible structure that gave shape to everything we see, from galaxies to galaxy clusters to the vast cosmic web itself. And here's the most staggering part. Dark matter might make up more than 5 times as much matter as all the ordinary stuff in the universe combined. That means that the stars, planets, moons, comets, gas clouds, and even you and me, all the things made from atoms, represent just a small fraction of what's really out there. So when we ask the question, what is the universe made of? We must answer humbly, mostly of things we cannot see. That is the invisible puzzle. The reason dark matter has captured the imaginations of scientists, dreamers, and stargazers alike. It's not just a gap in knowledge, it's a whisper from the cosmos, reminding us that for all we think we know, there is still an enormous mystery gently holding the universe together. And tonight, we begin our slow and thoughtful journey into that mystery, a journey through what we can't see, but know is there, shaping, supporting, and silently guiding the stars across the sky. Picture a galaxy, not just a bright blur in the night sky, but a vast, spiraling ocean of stars, hundreds of billions of them, all spinning in elegant unison. At first glance, it's easy to believe that such a majestic structure must be held together by the gravity of its stars, just as planets are held in orbit by the sun. But when astronomers looked more closely, they discovered something baffling. These galaxies shouldn't be holding together at all. Let's imagine one specific galaxy. Perhaps it's shaped like a graceful spiral, with a bright central bulge and long, winding arms stretching out into the dark. You'd expect the stars closest to the centre, where most of the visible mass resides, to orbit quickly, pulled strongly by the galaxy's gravitational core. And as you move farther from the centre, you would expect those outer stars to move more slowly, their orbits becoming more gentle and relaxed. That's what Newtonian physics tells us. It's what our solar system shows us. Mercury, which is close to the Sun, races through its orbit, while distant Neptune drifts far more slowly. This is called Keplerian motion, and for centuries it made perfect sense. But when astronomers actually measured the rotation speeds of stars in distant galaxies, what they found was something deeply surprising. The stars on the outer edges weren't slowing down. They were moving just as fast as those closer to the centre. In some cases, they were even accelerating slightly. It was as though the galaxy was spinning like a solid disk, as if there were an invisible force field keeping everything in place. This discovery was not subtle. The difference between expected motion and observed motion was vast. If only the visible matter, stars, gas and dust, were responsible for holding the galaxy together, those outer stars should have been flung into space like water droplets flying off a spinning wheel. But they weren't. They remained perfectly in orbit, held in place by something unseen, something massive, something essential. This unexpected behaviour led to a revolutionary idea. What if the visible parts of galaxies were just the tip of the iceberg? What if there was something far greater, something invisible, surrounding and penetrating these galaxies, quietly anchoring their spinning stars? Astronomers began to envision dark matter halos, vast spherical regions of unseen mass that envelop each galaxy. These halos didn't shine, didn't absorb, didn't reflect, but they exerted gravity, and they were enormous. In fact, according to models, these halos were far larger than the galaxies themselves. They stretched out far beyond the last visible star, like a ghostly cloud silently guiding the cosmic dance. It's important to understand just how dramatic this is. Without dark matter, galaxies as we know them couldn't exist. The spinning of stars at such high speeds should tear galaxies apart, unless something extra is present to hold them together. That something extra must account for most of the galaxy's mass. Not just a small percentage, but sometimes up to 90%. That means when we look at a galaxy, we're only seeing about 1/10 of what's really there. The visible stars, though breathtaking, are like the lights on a distant city skyline. They outline the shape of something much larger and more complex beneath the surface. And that hidden structure is composed of dark matter. This phenomenon isn't isolated to just one galaxy. It's been observed again and again in countless spiral galaxies across the universe. It's consistent, it's measurable, and it's deeply unsettling because it means that almost everything we can see in the universe is surrounded and stabilized by something we can't see. Scientists tested every alternative explanation they could think of. Was there a problem with the data? Were the stars somehow influencing each other in unexpected ways? Could our understanding of gravity itself be flawed? While some of these possibilities are still being explored, none have explained the observations as simply and effectively as dark matter. And so, quietly and reluctantly, the scientific community began to accept the presence of this invisible mass. Not because they wanted to believe in ghosts of the cosmos, but because the evidence left no other path. Galaxies, especially spirals, had become the clearest laboratories for studying dark matter. Their stars, spinning faster than they should, pointing again and again to the same conclusion. The universe was whispering a secret. That there's more than meets the eye. That the forces holding things together are not always visible. That galaxies, those graceful, spiraling beacons, owe their very structure to a presence we cannot detect directly. In a way, there's something poetic about that. That the beauty we admire in the night sky, the sweeping arms of distant galaxies, the glowing clusters of stars, is made possible by an unseen hand. Dark matter doesn't dazzle. It doesn't sparkle. But it supports. It protects. It holds things in place, quietly and patiently, while the rest of the universe dances in the light. And so, while galaxies continue their silent spinning across the cosmic sea, we remain here on Earth, watching, wondering, and slowly piecing together a story that may one day reveal the full shape of the invisible. Until then, we gaze upward into the soft glow of the Milky Way, knowing that behind every star there is a mystery holding it in place. To truly understand the role of dark matter in our universe, we must follow a quiet but powerful force that governs the movements of stars, planets, and galaxies alike. Gravity. Gravity is the silent architect of the cosmos, gently pulling together gas clouds to form stars, guiding planets around suns, and choreographing the motions of entire galaxies. It's not flashy, not loud, but it is everywhere, and it always leaves its signature. And it is through gravity that dark matter first began to betray its presence. Imagine being an astronomer, peering deep into the sky, watching galaxies drift and whirl through space. You know that gravity is what binds things together. The more mass something has, the more gravity it exerts. That's why Earth holds you down, why the moon orbits Earth, and why the Earth orbits the Sun. So naturally, when you look at a galaxy, you expect that its motion, its speed, its stability must be the result of the mass you can see, its stars, its planets, and its clouds of gas. But something strange happens when you start to measure those movements with precision. Let's take the example of a galaxy again. If you were to calculate how much mass is needed to keep the stars moving in the way they are, especially the stars far from the galactic centre, you'd come up with a certain number. Then you'd look at all the visible matter in the galaxy. How many stars there are? How much gas? How much dust? And when you add it all up, it falls drastically short. It's not a small error. The galaxy appears to need 5 times more mass than what we can account for, just to keep the stars from drifting away. This discrepancy is what scientists call the missing mass problem. It's as if the galaxy is performing a balancing act, spinning rapidly but not flying apart, and yet the safety net holding it together is invisible. It's not just an academic problem, it's a profound clue that something we don't understand is at work, hiding in plain sight. Now, let's expand our view beyond a single galaxy. When astronomers looked at galaxy clusters, enormous gatherings of hundreds or even thousands of galaxies, they ran into the same issue. The galaxies within these clusters were moving too quickly to be held together by the visible matter alone. Without something more, the clusters should simply disband over time, like a swarm of bees dispersing into the wind. But they don't. The clusters stay intact, even over billions of years. So once again, gravity suggests there must be more mass there than what we can see. And once again, dark matter steps in as the silent, invisible explanation. Perhaps the most compelling evidence comes from something called gravitational lensing. This is a phenomenon predicted by Einstein's theory of general relativity. It states that mass can bend space, and when space is bent, light travelling through it also bends. So if you have a massive object, like a galaxy cluster, sitting between you and something even farther away, the cluster can bend the light of the distant object, creating distorted or magnified images. It's a bit like looking at the world through a wine glass. By carefully studying these distortions, astronomers can map the mass of the intervening object, even if much of it is invisible. What they found was stunning. The amount of mass required to bend the light in the way they observed was far greater than the mass of all the visible matter in the cluster. The gravity was real, the lensing effect was real, but most of the mass causing it was unseen. These gravitational distortions offered scientists a way to see the dark matter, not directly, but through its influence. It's like watching trees sway in the wind. You can't see the air, but you know it's there because of how it moves the world around it. Dark matter is the wind of the cosmos, and gravity is the motion it leaves behind. Even more intriguingly, some of the strongest pieces of evidence come from collisions between galaxy clusters. One famous example is the Bullet Cluster, a pair of colliding galaxy clusters observed in the constellation Carina. During the collision, the hot gas from each cluster, which contains most of the visible mass, was slowed down and disrupted by the interaction, but gravitational lensing showed that the majority of the mass had passed straight through the collision unaffected. It hadn't been slowed or stopped like the gas. This invisible mass kept moving forward, as if it were made of ghostly particles that didn't interact with normal matter at all. This observation was a turning point. It strongly suggested that whatever dark matter is, it behaves very differently from ordinary matter. It doesn't collide, it doesn't heat up, it doesn't scatter, it just passes through. But it does exert gravity, and that gravity is measurable. And so, through the careful study of motions, of gravitational lensing, and of galactic collisions, scientists have come to a sobering conclusion. There is far more to the universe than meets the eye. In fact, all the galaxies, stars, planets, and atoms, the entire visible universe, make up only about 5% of the total. About 27% is dark matter, and the remaining 68% is something even more mysterious: dark energy, which we'll leave for another dreamy night. But for now, dark matter remains our focus. It is gravity's silent fingerprint on the cosmos, a presence we can't touch, can't see, and yet can measure by its gentle pull on the things we can see. It reminds us that the universe is deeper, more mysterious, and more beautiful than we ever imagined, and that sometimes the most powerful truths are hidden in silence and shadow. When we think about solving a mystery, we often imagine uncovering clues, evidence that points toward what something is. But in the case of dark matter, one of the most revealing strategies scientists have used is the opposite: figuring out what it isn't. This method, ruling things out one by one, is like walking through a quiet house at night, gently opening every door, only to find each room empty. Slowly, patiently, the possibilities grow fewer, and the shape of the unknown becomes a little more clear. At first, scientists wondered if dark matter might just be ordinary matter that we couldn't see. Things like cold clouds of gas, or planets that don't shine. After all, not everything in space is brightly lit. Could it be that the missing mass was simply made of dim, undetectable objects? These candidates were given a name: MACHOs, short for Massive Compact Halo Objects. They included things like faint stars, black holes, and rogue planets drifting alone through the space. It was a tempting idea. These were things we knew existed. Perhaps there were just more of them than we realized. To test this theory, astronomers turned to a clever technique called gravitational microlensing. When a macho passes in front of a distant star, its gravity can bend the starlight and briefly make the star appear brighter, just for a moment. By observing large numbers of stars over time, astronomers hope to detect these brightening events and count how many machos were floating around unseen. What they found was fascinating and disappointing. The microlensing events were rare, far too rare to explain the amount of dark matter needed. There simply weren't enough of these objects to account for the gravitational effects observed in galaxies and galaxy clusters. Majos might make up a small fraction of the universe's mass, but not nearly enough. That door, gently opened, was found to be mostly empty. Next, scientists looked to another familiar possibility: gas. Space is filled with enormous clouds of hydrogen and helium, the raw materials of stars. Perhaps dark matter was made of cold, invisible gas that hadn't yet condensed into stars, and therefore didn't emit light. But here too, there was a problem. Gas, even when cold, can be detected through other means, particularly through radio waves and X-rays. And if there were enough gas to account for all the missing mass, it would be glowing in those wavelengths. But it wasn't. The sky remained too quiet. So the idea of dark matter as dark gas faded like mist in the morning sun. The next theory took a more radical turn. What if dark matter wasn't made of atoms at all? What if it was something fundamentally different? Non-baryonic matter. Baryons are the particles that make up atoms, protons and neutrons. This idea opened up a whole new realm of possibilities, and with it, a new generation of candidates. Particles that don't exist in the everyday world we know. One of the leading ideas is the existence of WIMPs, or weakly interacting massive particles. These are hypothetical particles that have mass, and therefore gravity, but barely interact with regular matter. A WIMP could pass right through the Earth, through your body, through an entire planet, and you would never notice. They would be invisible, not because they're hiding, but because they don't engage with light or atoms in any noticeable way. If WIMPs exist, they could form enormous halos around galaxies, explaining all the gravitational effects without ever giving off a single spark of light. Other strange possibilities emerged as well. Axions, for example, are ultralight particles that could exist in a massive number and subtly influence the structure of space. Unlike WIMPs, which are heavier and fewer, axions would be almost weightless, but extraordinarily abundant. Together, their collective gravity could shape the universe. Despite decades of searching, none of these particles have yet been directly detected. Experiments deep underground, shielded from cosmic rays and background radiation, are running quietly, hoping for a single interaction. A tiny flash, a tiny bump, a whisper from the invisible world. But so far, the silence remains. There were other ideas too, growing more exotic. What if dark matter were made of sterile neutrinos? A mysterious form of neutrino that doesn't interact with any known forces except gravity? What if it was made of primordial black holes, born in the earliest moments after the Big Bang, too small and scattered to detect easily? What if it wasn't even matter at all, but rather a sign that our understanding of gravity itself is incomplete? That last possibility opened a bold new door. Perhaps we don't need to add something invisible. Perhaps we need to rewrite the rules. Theories like modified Newtonian dynamics, MOND, suggested that gravity behaves differently on large scales than we expect. Maybe gravity grows stronger at vast distances, enough to account for the strange motions of stars and galaxies. But while MOND can explain some galactic behaviours, it struggles to match the full range of cosmic evidence, especially the gravitational lensing observed in galaxy clusters. And so, again and again, the universe gently narrows our path. It tells us, it is not this, it is not that. Try again. In ruling out what dark matter is not, we have learned much more than we might have expected. We've discovered the limits of familiar matter. We've measured the boundaries of gas and dust and stars. We've tested the known and imagined the unknown. In the process, we've refined our instruments, deepened our models, and expanded our curiosity. Dark matter remains elusive, but its presence is undeniable. It hides not because it wants to, but because its nature may lie beyond the reach of light, beyond the grasp of atoms, in a realm where gravity is the only messenger. And so, we continue the search, turning down one corridor after another in this silent, cosmic house. Each empty room teaches us more about the architecture of the whole. Each closed door brings us closer to the one that finally opens, quietly, unexpectedly, into the invisible heart of the universe. Sometimes, the beginning of a great mystery lies not in a breakthrough, but in a question that refuses to go away. In the 1930s, a Swiss astronomer named Fritz Zwicky stood before such a question, one that would echo through the next century of astrophysics. Working at the California Institute of Technology, Zwicky turned his gaze not just to stars or individual galaxies, but to entire galaxy clusters, enormous collections of galaxies bound together by gravity, floating together through the vast darkness of space. One such cluster was the Coma cluster, a brilliant and massive gathering of over 1,000 galaxies, located about 320 million light-years away in the constellation Coma Berenices. To the naked eye, the Coma cluster is invisible, but through the powerful telescopes of the time, it was a treasure trove of motion, energy, and puzzling behaviour. Zwicky, ever curious and famously bold, began to study how these galaxies moved. What he found would quietly shake the foundations of astronomy. To measure the mass of a galaxy cluster, scientists can observe how fast the galaxies within it are moving. Faster motion usually means more mass is present to keep the system gravitationally bound. It's like watching bees fly around a hive. If they're moving quickly but staying near the centre, you assume something strong is holding them in place. Zwicky applied this logic using the virial theorem, a mathematical tool from physics that relates the average speed of objects in a system to the total mass holding that system together. But when he plugged in the data, when he compared how fast the galaxies in the Coma cluster were moving to how much visible matter there was, he got a result that didn't make sense. The galaxies were moving too fast. In fact, they were moving so fast that by all accounts the cluster should have flown apart long ago. The gravitational pull from the visible matter, the stars, the dust, the galaxies themselves, was nowhere near strong enough to hold the cluster together at those speeds. Zwicky did not shy away from the contradiction. He proposed something radical. What if there was a large amount of invisible matter in the cluster? Something we couldn't see, but that exerted gravitational force. He called this unseen substance Dunkel Materia, German for dark matter. At the time, few took this suggestion seriously. Zwicky was a brilliant thinker, but he was also known for his unconventional ideas and confrontational personality. His peers largely set aside the dark matter idea, considering it an odd proposal from an eccentric mind. After all, the data available was limited, and the concept of missing mass seemed, to many, more like a measurement error than a cosmic secret. And yet, Zwicky's numbers were correct. What he had uncovered, decades before it would gain widespread attention, was the first clear sign that the universe contained far more than meets the eye. The Coma Cluster was the first astronomical system that told us visible matter is not enough. There is something else holding the cosmos together. Over the years, Zwicky's work gained quiet support as better data and more advanced instruments became available. Other astronomers began to see similar discrepancies in different clusters, and even in individual galaxies. Slowly, Zwicky's once dismissed idea began to take on the weight of evidence. The story of the Coma Cluster reveals something profound about the scientific process. At first, the idea of dark matter was not born in triumph or celebration. It was born in doubt, in data that didn't fit, in questions that refused to go away. Zwicky didn't discover dark matter by looking for it. He discovered it by refusing to ignore a contradiction. He also reminded us that sometimes the universe doesn't behave the way we expect, not because we're wrong about everything, but because we're missing something essential, something we can't yet see. The Coma Cluster continues to be studied today, with modern instruments far more sensitive than those Zwicky could ever have imagined. X-ray telescopes have revealed hot gas that fills the space between galaxies, but even that visible matter doesn't account for the gravitational pull observed. Modern measurements confirm what Zwicky saw. Most of the cluster's mass is still invisible. Today, Zwicky's early work is seen as prophetic. Though his ideas were ahead of their time, they opened the door to an entirely new way of thinking about the universe. Dark matter isn't just an adjustment to existing models. It's a whole new chapter in our understanding of reality. And it began, in part, with a man who looked at the stars, saw how they moved, and dared to ask, what's holding them there? In the quiet mystery of the Coma Cluster, the universe whispered its secret for the first time. A secret that, to this day, we are still trying to fully understand. And though Zwicky didn't have all the answers, he had the courage to listen. In the stillness of the night sky, galaxies appear as silent spirals of light, eternal, graceful, and calm. But deep within their glowing arms, something strange is happening. Their stars are spinning, some faster than they should, some holding position against impossible odds. And watching this, decades after Fritz Zwicky first pointed to the mysterious presence of unseen mass, another astronomer stepped forward to listen more closely to the whisper of the stars. Her name was Vera Rubin, and her work would transform our understanding of the cosmos forever. In the mid-50s, Rubin, working alongside her colleague Kent Ford, undertook a meticulous study of spiral galaxies. Where Zwicky had looked at galaxy clusters, Rubin focused on individual galaxies themselves. She wasn't interested in grand cosmic collisions or dramatic galaxy mergers. She wanted to know something simple, something almost childlike. How fast do stars orbit within their own galaxies? Using powerful spectrographs, she measured the rotation curves of spiral galaxies. A rotation curve is a graph that shows how fast stars are moving at different distances from the galaxy's centre. If galaxies followed the same physical laws as our solar system, the curve would rise quickly in the inner regions, where most of the mass lies, and then fall off as you move outward. In our solar system, for example, Mercury races around the Sun at incredible speed, while distant Neptune creeps along its orbit much more slowly. The farther a planet is from the Sun, the weaker the gravitational pull it feels, and the slower it moves. Rubin expected to find something similar in galaxies, stars near the centre spinning rapidly, and those near the edge moving more slowly, governed by the gravitational pull of the galaxy's visible mass. But what she found was startling. Instead of falling off, the rotation curves remained flat. Stars far from the centre were moving just as quickly as those near it. It was as though the galaxies were spinning like solid disks, not like systems governed by gravity alone. These stars weren't slowing down. They weren't fading into silence. They were racing along at high speeds, far from the core, where there was seemingly not enough visible mass to hold them in place. Rubin double-checked. Then she triple-checked. She and Ford gathered data from dozens of galaxies. The pattern repeated itself again and again. The outer stars were too fast. The galaxies should have been tearing themselves apart, but they weren't. Something was holding them together. Something massive, invisible, and spread far beyond the visible edges of the galaxies. This was more than an anomaly. This was a cosmic contradiction. Rubin's work provided the most convincing and widespread evidence yet that dark matter wasn't just a peculiarity in galaxy clusters like Zwicky had found. It was everywhere. It was in the very structure of galaxies. It was shaping their motion, sculpting their form, anchoring their stars. And it wasn't a rare phenomenon, it was universal. The implications were staggering. If galaxies all needed extra, invisible mass to stay intact, then dark matter wasn't just a curiosity, it was a fundamental component of the universe. Rubin's rotation curves became one of the most important pieces of evidence in support of dark matter. Her work solidified what had once been a fringe idea into the heart of modern cosmology. But Rubin's contribution went beyond just data. It was her persistence, her clarity of thought, and her refusal to dismiss the unexpected that helped shift scientific opinion. In a time when women were still often sidelined in astronomy, she pursued her work with patience, grace, and unrelenting precision. She famously said, "Science progresses best when observations force us to alter our preconceptions." And with every galaxy she measured, Rubin was doing just that, forcing the scientific world to acknowledge that the universe was not what it appeared to be. Through her eyes, dark matter became something real. Not just a placeholder in equations, but a vast, invisible structure, an unseen scaffolding that cradles galaxies in space. She showed us that the light we see is only part of the story, that beyond the glow of stars lies a deeper truth, one that only gravity can reveal. Today, every astronomy textbook includes the flat rotation curves Rubin discovered. Her name is spoken with reverence by scientists who recognize how profoundly she changed our understanding of the cosmos. And yet, her work leaves us with questions still unanswered. What is this dark matter? What is it made of? Why does it refuse to shine? Rubin didn't claim to know. She didn't pretend to offer final answers. But what she did do, patiently, brilliantly, and quietly, was to show the universe for what it is, deeper, stranger, and more mysterious than we ever imagined. When we look up at the Milky Way, winding its pale ribbon across the night sky, we see only the surface. Rubin taught us to look beneath that surface, to listen to the spin of stars, to pay attention to the motion of things we cannot see. And in that motion, in that rhythm, the ghost of dark matter whispers to us still. When we gaze up at the night sky, what we see is breathtaking. Stars scattered like diamonds across a canvas of black, glowing nebulae, the faint swirl of distant galaxies. All of this, the visible universe, is majestic, vast, and seemingly infinite. And yet, as beautiful and expansive as it appears, it makes up only a tiny fraction of what truly exists. In fact, everything we can see with our eyes, telescopes, and detectors, all the stars, planets, dust, and galaxies, accounts for less than 4 of the total matter and energy in the universe. That means more than 95% of the cosmos is invisible to us. And of that, roughly 27% is believed to be dark matter. This realization came slowly, and with considerable resistance. For generations, astronomers assumed that the stars we could see were the main actors in the cosmic story, that galaxies were composed primarily of the glowing matter visible through telescopes. But as more precise observations were made, especially in the 20th century, the numbers began to paint a different picture, one that didn't quite add up. When scientists measured the gravitational pull required to hold galaxies and galaxy clusters together, they found that the visible mass was insufficient by a wide margin. The motions of stars within galaxies, the movement of galaxies within clusters, and the bending of light around massive objects all told the same tale. There is far more mass present than what we can detect directly. And so, a staggering conclusion began to emerge. The majority of the matter in the universe is not made of atoms. It's not made of anything that emits light, absorbs light, or reflects light. It doesn't burn like stars, float like gas clouds, or clump together like planets. It is something different, utterly invisible to electromagnetic radiation. And yet it gravitates. It pulls. It shapes. It molds the universes on the grandest of scales. Scientists began mapping this hidden matter, not by seeing it, but by tracing its influence. In places where gravity was stronger than expected, they inferred that dark matter must be present. In regions where galaxies spun faster than physics allowed, they concluded that dark matter was there, anchoring those stars. Through these methods, astronomers built vast, invisible maps of the cosmos, maps of things they could not directly observe. One of the most powerful tools for this mapping is gravitational lensing, the bending of light around massive objects. When we look at the light from very distant galaxies and see it distorted in strange and beautiful ways, we're often seeing the effects of dark matter between us and those galaxies. The gravity from this unseen mass bends the light, much like the curvature of glass bends an image. And by studying these distortions, scientists can determine just how much mass is in that region of space. Again and again, the results are the same. The mass we see is only a small fraction of the mass that's actually there. This leads to one of the most profound facts in modern cosmology. Most of the matter in the universe is dark matter. It's not just a small correction to our models. It's not a hidden corner of physics. It's the dominant form of matter in existence. If you gathered all the stars in all the galaxies in the universe, added in every planet, every asteroid, every comet, every gas cloud, everything we've ever seen, you still wouldn't come close to matching the amount of mass inferred from gravitational effects. It's humbling, it's mysterious, and it's absolutely real. In fact, without dark matter, the universe wouldn't look anything like it does today. Galaxies might never have formed. The structures we see, the cosmic web of filaments and voids that stretches across billions of light years, wouldn't have come together. In the early universe, ordinary matter moved too quickly, too energetically, to clump together on its own. But dark matter, cold and slow-moving, began clustering first. Its gravity provided the scaffolding on which the visible universe could grow. Dark matter shaped the galaxies before they ever shone. It created the gravitational wells that pulled gas inward, allowing stars to ignite. It determined the large-scale structure of the cosmos, not as an afterthought, but as the quiet foundation for everything else. And yet, we cannot touch it. We cannot see it. It may pass through your body right now, through the Earth, through entire planets and stars, without ever interacting in any detectable way. It doesn't seem to be made of atoms. It doesn't carry electric charge. It doesn't emit heat. It's like a ghost substance that surrounds us completely, and still slips through our grasp. Scientists call this the non-baryonic nature of dark matter. Ordinary matter, what you, I, and all stars are made of, is a baryonic. It consists of protons, neutrons, and electrons. But dark matter seems to be of a different order, one that belongs to a separate class of particles, a kind of matter that existed in the early universe, formed side by side with baryonic matter, but took a different path, one that led it away from light and into silence. This revelation has changed how we view the universe. No longer can we assume that what we see is what we get. The cosmos is not a theatre lit only by stars. It is a shadowed cathedral with invisible architecture holding the visible world in place. The galaxies are not isolated islands. They are luminous ships floating in a vast, unseen sea. Even now, as we map the cosmos, we are mostly charting the presence of something we can't see. The most detailed surveys of the universe, like the Sloan Digital Sky Survey or the Dark Energy Survey, rely on tracing the distribution of dark matter to understand the shape and history of everything else. It's like studying a painting by following the brushstrokes you can't see, but whose influence is everywhere on the canvas. And so, as you look up into the night sky and marvel at the stars, remember that they are only a small part of a greater whole. For every glowing point of light, there is a vast and invisible companion, guiding it, anchoring it, giving it form. The stars shine in the light, but the universe is built in the dark. If you were to reach out and hold a pebble in your hand, you would be holding something made of what physicists call ordinary matter. Atoms composed of protons, neutrons, and electrons. This is the type of matter that builds everything we know. The air we breathe, the water we drink, the stars above, and even the galaxies that drift through the universe. It's tangible, familiar, and observable. But here's the astonishing part. This kind of matter is rare. As we now understand, most of the universe, especially its mass, is not made of ordinary atoms at all. Instead, it's composed of something invisible and silent, dark matter. And to comprehend the mystery of dark matter more deeply, it helps to understand how it differs from the matter we know so well. Ordinary matter, also called baryonic matter, gets its name from baryons, particles like protons and neutrons. These particles clump together to form atomic nuclei, and with electrons added in, they form atoms. Atoms, in turn, combine into molecules, and molecules become the building blocks of all the things we see and touch. Rocks, trees, animals, planets, and stars. One of the defining traits of ordinary matter is that it interacts with light. That's why we can see it. Light reflects off the surface of the moon. It shines through clouds of interstellar gas. It glows from stars, is absorbed by dust, and can even be bent by gravitational forces. Every observation we make using telescopes, whether they collect visible light, infrared, ultraviolet, or X-rays, is based on this basic interaction. Ordinary matter reveals itself by how it engages with the electromagnetic spectrum. Dark matter, however, is invisible in this way. It does not emit, reflect, or absorb light. No telescope, no matter how advanced, can take a direct image of it. If a cloud of dark matter passed right in front of a bright star, the star's light would continue to shine, undimmed, unbent, unchanged, unless of course the dark matter's gravity subtly distorted the light, which is one of the few ways we can detect it. But invisibility is only the beginning. Ordinary matter not only interacts with light, it also interacts strongly with itself. When two atoms come close together, their electric fields interact. That's why you can't push your hand through a solid wall. It's not because the atoms are touching in the literal sense, but because their electrons repel each other. That's electromagnetism at work. Dark matter seems not to experience electromagnetic forces. It does not form atoms. It doesn't clump into stars or planets. It doesn't absorb energy the way ordinary matter does. It doesn't heat up, cool down, or radiate. And when two clouds of dark matter collide, they pass right through one another, barely noticing. It's like fog drifting through fog. This difference in interaction is profound. Ordinary matter is messy. It collides, compresses, heats up, and glows. Dark matter is quiet, unaffected by light, barely influenced by anything but gravity. It's the loner of the universe, exerting force but refusing to be touched. And yet, despite this silence, it holds more mass than all the baryonic matter combined. Based on the best measurements from satellites like WMAP and Planck, we now know that dark matter makes up about 27% of the universe's mass energy content, while ordinary matter only accounts for about 5%. The rest, incredibly, is something even more mysterious: dark energy, which we'll explore another time. But how do we know that dark matter is truly different from ordinary matter, and not just more of the same hiding in dark corners? One compelling clue comes from the study of the cosmic microwave background, the afterglow of the Big Bang. This ancient radiation carries with it a subtle pattern, like ripples on the surface of a pond, that tells us how matter was distributed in the early universe. If all matter had been baryonic, the pattern of these ripples would look very different. But the pattern we observe shows that there was a large amount of matter that didn't interact with light even back then. This invisible matter must have been present from the earliest moments of cosmic time, and it couldn't have been made of atoms. Other observations confirm this. In galaxy formation simulations, when scientists use only ordinary matter in their models, the galaxies don't form properly. The universe ends up looking too smooth, too fragile, with galaxies forming too late or not at all. But when dark matter is included, acting as a silent gravitational web, the universe we see today suddenly comes into focus. The simulations begin to look like reality. It's as though dark matter created the framework of the universe. Like steel beams in a skyscraper, it provided the invisible scaffolding for galaxies to build upon. Ordinary matter followed the gravitational paths carved by dark matter, falling into the invisible wells, forming stars and worlds and eventually us. And yet, despite how much we owe to it, dark matter remains entirely other. It doesn't form atoms. It doesn't burn. It doesn't shine. It doesn't build. It shapes and it guides, but from behind the curtain. There is a haunting beauty in this duality. Ordinary matter is the performer, dancing, glowing, changing. Dark matter is the silent stagehand, supporting, directing, and anchoring the entire performance, but never stepping into the light. This difference between matter that interacts with light and matter that does not is perhaps the greatest divide in all of physics, and for now, it defines the boundary between what we know and what we still don't. As we continue to study the universe, new experiments, deep underground, far out in space, in particle accelerators, and in quiet mountain laboratories, are all searching for that one signal, that one whisper from the dark, a sign that will tell us not just that dark matter is different, but what it truly is. Until then, we live in a cosmos where the visible is shaped by the invisible, where the known is surrounded by the unknown, and where the most familiar matter in existence, what we're made of, is only a small, flickering light in a vast, silent sea of the unseen. In a universe filled with light, it seems almost paradoxical that so much of what exists is invisible. We navigate the cosmos using the tools of light, telescopes that collect it, instruments that split it into spectra, sensors that capture it in every wavelength from radio to gamma rays. These tools allow us to see the births of stars, the collisions of galaxies, and the remnants of supernovae glowing in the silence of space. But when it comes to dark matter, light refuses to cooperate. Dark matter does not emit light. It does not reflect it, absorb it, or scatter it. And yet, it is there, present in such abundance, that it outweighs all the luminous matter in the universe. This raises a haunting question. If we cannot see dark matter directly, how do we know it's there at all? The answer lies in the delicate footprints it leaves behind, indirect evidence that builds a powerful case. While dark matter may never show up in a telescope image, its presence bends light, sculpts the cosmos, and tugs gently on the stars. And by studying these subtle effects, we can begin to map the invisible. One of the clearest ways we detect dark matter's presence is through gravitational lensing. According to Einstein's theory of general relativity, massive objects warp the fabric of space-time. Light, though it travels in straight lines through empty space, will curve if it passes through a region where space-time is bent by gravity. When we observe light from a very distant galaxy or quasar that passes near a massive foreground object, like a galaxy cluster, the light can bend around it, creating arcs, rings, or multiple distorted images of the background object. This phenomenon is known as gravitational lensing, and it has become one of the most powerful tools for uncovering the distribution of dark matter. Here's the key. When astronomers calculate how much visible matter exists in the lensing object, they find it's not enough to account for the amount of distortion in the light. Something else must be contributing to the gravity that bends the light. And when they map the lensing effects carefully, they discover that the invisible mass responsible for the additional gravity is dark matter. In some cases, the visual evidence is breathtaking. The Bullet Cluster is a famous example, a cosmic collision between two galaxy clusters. When the clusters collided, the hot gas between them, composed of ordinary matter, slammed together, slowing down and heating up. But gravitational lensing showed that the bulk of the mass had passed straight through the collision zone, unaffected by the impact. The visible matter had been disrupted. The dark matter had not. It continued on its path, interacting only gravitationally, leaving the ordinary matter behind. This separation between visible matter and gravitational mass provided direct observational proof that dark matter behaves differently than ordinary matter, and that its presence can be independently inferred through gravitational effects. Beyond lensing, we also detect dark matter through its influence on the motions of stars and galaxies. In spiral galaxies, the stars far from the centre orbit at speeds that defy explanation. If only the visible matter were present, the stars at the edges would drift away, pulled too weakly by gravity to remain in place. But they don't. They orbit as if they're embedded in a massive, invisible halo of matter. When astronomers plot the rotation curves of these galaxies, graphs showing how orbital speeds change with distance, they find that the curves remain flat instead of falling off. This flatness is a clue, a quiet hint whispered by the stars themselves. Something else is here. Galaxy clusters tell a similar story. By studying how galaxies move within clusters, how they fly, swirl, and orbit, astronomers can calculate the gravitational mass required to keep the cluster together. The visible mass is only a fraction of what's needed. The rest is inferred, dark matter again, stabilizing structures far larger than any one galaxy. Another subtle clue comes from the cosmic microwave background, the faint afterglow of the Big Bang. This radiation bathes the entire universe, a nearly uniform sea of light from when the universe was only about 380,000 years old. But it's not completely uniform. It contains tiny temperature fluctuations, like ripples in a calm lake. These ripples are imprints of the early density variations in the universe, seeds from which galaxies would grow. By analysing these patterns, especially with missions like WMAP and Planck, scientists can determine the composition of the early universe with remarkable precision. The patterns would look very different if the only matter present were baryonic. The data show clearly that most of the matter at that time, as now, was non-baryonic, matter that does not interact with light, dark matter, written in the sky's oldest light. Then there's structure formation. the process by which small density fluctuations in the early universe grew into galaxies, clusters, and superclusters. Simulations of the universe's evolution that include only ordinary matter fail to produce the structures we see today. Ordinary matter alone is too energetic, too interactive. It resists collapse. But when dark matter is added, cold, invisible, unreactive, it begins to clump early, forming the gravitational scaffolding that pulls ordinary matter in. The resulting structures match observations. Without dark matter, the universe would be too smooth, too uneventful. It would not look like this. All of this points to a profound truth. While we may not see dark matter directly, its effects are everywhere. It acts not as a silent spectator, but as a shaper of worlds, leaving subtle imprints on the sky for those who know where to look. Yet perhaps the most haunting part of all is this: we are surrounded by it. Dark matter is not a distant phenomenon, locked away in far galaxies or ancient radiation. It is believed to pass through our galaxy, our solar system, even our very bodies, every moment of every day. Vast clouds of it orbit the Milky Way. Particles of it may be streaming through the Earth as you read these words. But because it interacts so weakly, we do not feel it. We do not touch it. We cannot see it with our eyes. And yet, through gravity's quiet pull and light's gentle curve, we know it's there. In the end, we have become explorers of the invisible landscape of the universe, mapping what cannot be seen, listening to echoes instead of voices, studying the shadows cast by things that cast no light. And in doing so, we uncover a truth more strange and more beautiful than anything we could have imagined, that most of what exists is hidden, yet not silent, invisible, yet not absent, dark, yet full of meaning. Despite all we've learned about dark matter, its gravitational pull, its presence in galaxies and clusters, its ability to shape the structure of the cosmos, we are still left with the most essential question: what is it actually made of? We know what it does. We see its effects. But we don't yet know what it is. It's like hearing footsteps in an empty room. Something is there, but it refuses to show itself. So scientists have spent decades building theories and designing experiments in an effort to reveal the true identity of dark matter. The candidates are many, some simple, some exotic, and some nearly impossible to imagine. These theories don't arise from wild speculation, but from carefully guided logic, based on everything we've observed about dark matter's behaviour. It must have mass. It must exert gravity. It must not interact with light. And it must not collide or clump like normal matter. One of the most well-known and promising candidates is something called a WIMP, a weakly interacting massive particle. The idea is almost elegant in its simplicity. WIMPs are particles that have mass, meaning they feel the tug of gravity, but they interact so weakly with other forms of matter that they pass through almost everything unnoticed. A single WIMP could pass through the entire Earth without ever touching an atom. WIMPs are theoretical, but they fit beautifully into many particle physics models. In fact, some versions of supersymmetry, a proposed extension to the standard model of particle physics, predict the existence of such particles naturally. If true, the early universe would have created vast numbers of WIMPs shortly after the Big Bang. These particles wouldn't clump or glow, but their sheer mass would allow them to quietly shape the cosmos over billions of years, and so scientists built detectors, massive, sensitive instruments located deep underground, shielded from cosmic rays and radiation, in hopes of catching a single interaction between a WIMP and an atom. These detectors are placed in former mines, in mountains, and even under the ocean floor, filled with ultra-pure liquids and surrounded by sensors, all awaiting for a faint flash, a quiet tap, a ripple from the dark. But so far, the detectors have remained quiet. This has led researchers to consider other possibilities. Another leading candidate is the axion, a particle far lighter than a WIMP, so light in fact that it may act more like a wave than a particle. Axions wouldn't be created through the same mechanisms as WIMPs. Instead, they would form a kind of cosmic field spreading throughout the universe like an invisible fog. Their interactions would be even weaker than WIMPs, but under the right conditions, they might convert into photons, particles of light, inside strong magnetic fields. This gives scientists a new path to detection, highly specialized experiments designed to observe those faint conversions. The search for axions has grown steadily more sophisticated, using microwave cavities, high field magnets, and ultra-sensitive detectors, hoping to hear that whisper from the dark. Just like with WIMPs, nothing has been confirmed, yet. But the silence only deepens the intrigue. Some theories take an even bolder approach. What if dark matter isn't a single type of particle, but a whole spectrum of them? Just as visible matter comes in many forms, electrons, protons, neutrons, quarks, perhaps dark matter is composed of an entirely hidden sector of particles, interacting with each other through forces we don't yet understand. This idea is known as the dark sector, a kind of mirror universe that overlaps with our own, invisible to us except through gravity. In these theories, there could be dark photons, dark atoms, even dark chemistry, entire invisible structures that we will never touch or see, but which move through us all the same. The very laws of physics might be more complex than we ever imagined, with entire forces and particles silently operating alongside our familiar universe. And then there are the even more exotic possibilities. Some physicists propose that dark matter might consist of sterile neutrinos, hypothetical versions of neutrinos that do not interact through the weak nuclear force, only through gravity. Others have suggested primordial black holes, formed just after the Big Bang, too small to observe directly, but numerous enough to account for a portion of the dark matter. These tiny black holes would be unlike the ones formed by stars. They'd be ancient, quiet, and almost impossible to detect. Yet their mass could help bind galaxies together. Each of these theories presents new questions, new avenues of research, and new types of experiments, from underground labs to high-altitude balloons, from satellite observatories to particle accelerators like the Large Hadron Collider. We are reaching into every corner of physics to find the nature of this invisible mass. And yet, despite the effort, dark matter has remained elusive. It continues to dance just out of reach, leaving behind its gravitational footprints, but never stepping into the light. No known particle in the Standard Model can account for it. This means that solving the mystery of dark matter could lead us to new physics. A discovery as profound as the realization that atoms exist, or that the universe is expanding. It may even redefine what we think of as matter. But the search is far from over. Each experiment that returns no results helps us rule out possibilities, refine models, and move closer to the truth. Science is patient, and the universe, in its own time, always reveals its secrets. What is dark matter made of? We still do not know, but we know it is not made of anything we've ever touched. It is not in the stars, not in the atoms, not in the light. It is something else, something fundamental. Perhaps it is a particle, perhaps a wave, perhaps a window into another layer of reality. Whatever it is holding us all together. It shaped the galaxies. It sculpted the stars. It made the universe what it is. And one day, when we finally identify it, not just by its pull, but by its presence, we will look back on this era, when the cosmos quietly whispered of a hidden world, and we listened. In the silent chambers of laboratories carved deep into the earth, shielded from the background noise of the cosmos, instruments wait. Not for thunder, not for fire or light, but for the faintest of whispers. An almost unimaginable interaction between ordinary matter and something far stranger, the mysterious particles that may make up dark matter. Among the most studied candidates in this search are particles known as WIMPs, weakly interacting massive particles. These hypothetical entities are considered perfect suspects in the case of the universe's missing mass. They have mass, so they can exert gravity, but they barely interact with the electromagnetic force, which means they don't emit or absorb light. That's why they remain invisible. But unlike truly ghost-like particles, WIMPs are still theorized to interact occasionally through the weak nuclear force, the same force responsible for radioactive decay. And that tiny interaction offers a tiny hope. Perhaps, just once, one of these particles might nudge an atom on Earth and leave behind a trace. To find that trace, scientists have constructed some of the most sensitive machines in human history. These direct detection experiments are typically placed deep underground, miles beneath the Earth's surface, in abandoned mines or custom-built facilities, hidden from cosmic rays and natural radiation that would otherwise overwhelm the delicate signals they are looking for. One such project is the Xenon experiment, located beneath a mountain in Italy. It uses a tank filled with thousands of kilograms of liquid xenon, a noble gas that glows faintly when struck. When a WIMP passes through the tank, and if it happens to bump into a xenon nucleus, it should produce a tiny flash of light and a ripple of electric charge. Sophisticated detectors surrounding the tank would capture both signals, allowing scientists to determine if a rare collision has occurred. Other experiments use different target materials: liquid argon, supercooled germanium, or cryogenic crystals. Projects like LIUX, PandaX, LZ, and Super CDMS are all variations on the same theme. Watch patiently, protect against every known source of interference, and wait for a single event that might change everything. But it hasn't happened, at least not yet. Despite decades of effort, no WIMP has been unambiguously detected. Some experiments have hinted at odd events, but none have passed the rigorous standards of repeatability and statistical certainty required for a confirmed discovery. The dark remains silent. So the search has expanded beyond WIMPs to stranger and more elusive possibilities. One of these is the axion, a theoretical particle that is vastly lighter than a WIMP. Unlike WIMPs, which might be detected through rare particle collisions, axions could behave more like a pervasive cosmic field. They may be everywhere, rippling gently through space like a hidden wind. Axions are predicted to have a peculiar property. In the presence of a strong magnetic field, they could convert into photons, particles of light. This opens a new method of detection. Rather than wait for a collision, scientists can try to coax the axions into revealing themselves by passing them through intense magnetic fields and looking for the faint emergence of light. Experiments like ADMX, Axion Dark Matter Experiment, use resonant microwave cavities, sealed chambers where electromagnetic waves bounce and build up strength. These chambers sit within powerful magnets and are tuned with exquisite precision. If an axion were to convert into a photon inside the cavity, the detectors would pick up a tiny signal, like hearing a single drop of water in a vast, silent cave. Another technique being explored is helioscopes, telescopes designed not to look at stars, but to listen for axions coming from the sun. If axions are produced in the sun's core and convert to light in the presence of a magnetic field, we might catch them on Earth using these specially designed instruments. The CAST experiment at CERN is one such effort, using a repurposed particle accelerator magnet to focus on our star. And still, the silence continues. But the absence of results is not failure. Each experiment that rules out a particular mass range or interaction strength helps narrow the field. It is like mapping a forest by slowly eliminating every tree you've searched, knowing that the hidden creature you seek must still be out there. As these direct and indirect searches expand, some scientists are looking elsewhere, toward colliders like the Large Hadron Collider, LHC, at CERN. The idea here is not to detect dark matter passing through Earth, but to try to create it in high-energy collisions. When particles smash together at near light speeds, they release enormous amounts of energy, enough, potentially, to form new particles. If some of that energy disappears without explanation, if the products of the collision don't add up, it could be a sign that dark matter has been created and slipped away. It wouldn't leave a direct signal, but an absence, a missing piece of the puzzle. Detecting that absence, though, requires immense precision. So far, no confirmed dark matter particles have emerged from the LHC either, but the effort has inspired an entire new branch of theoretical physics: dark sector physics. These are models that go beyond WIMPs and axions and propose an entire hidden world of particles, dark photons, dark fermions, and even dark forces. Some of these particles might interact with each other, but remain isolated from ordinary matter, except through subtle gravitational effects or tiny mixing with known forces. These models have led to proposals for new types of detectors, new accelerator experiments, and new astronomical observations. One concept, called light-dark matter, suggests that the particles we're searching for are not heavy at all, but feather-light, and that our previous searches simply weren't sensitive enough to detect them. Other experiments have gone cosmic. Instead of waiting for dark matter to come to us, they look into space, watching for indirect signs that dark matter might be annihilating or decaying into detectable particles like gamma rays or neutrinos. Telescopes like Fermi, AMS-02 and HESS have all searched the sky for these signals, scanning the centre of the Milky Way, dwarf galaxies and galaxy clusters. There have been intriguing hints, glows where none were expected, but no definitive confirmation. Still, the effort continues, like a long meditation under the stars. We may be centuries from a final answer, or we may be just one unexpected signal away. It's possible that dark matter is even stranger than we imagine, something that won't be found in any detector or experiment we currently possess. Or perhaps, like the Higgs boson, it's waiting patiently in the data, buried in noise, until the right eyes uncover it. In the meantime, science advances not just through discovery, but through the dedication to look, to listen, to refine, to question. And as we seek dark matter, through deep caverns, powerful magnets, distant stars and high-energy collisions, we are doing more than just solving a cosmic mystery. We are learning the value of patience, the beauty of silence, and the astonishing possibility that the greatest truths of the universe are not in the light, but in the spaces in between. The search for dark matter has spanned continents and decades, employed the most sensitive detectors and the brightest minds, and ventured deep into the silence of space and the heart of matter itself. And yet, despite our most diligent efforts, it remains hidden. So we are left with a difficult question, one that science has had to ask many times throughout its history. What if we're looking in the wrong place? What if our assumptions are flawed? What if dark matter doesn't exist at all? This idea may seem radical, even heretical, given the mountain of evidence pointing toward the gravitational effects of unseen mass. But science thrives on doubt, on the willingness to challenge its own foundations. And so, some physicists and cosmologists have dared to consider the possibility that dark matter might not be a new kind of particle, but rather a sign that our current understanding of gravity is incomplete. This line of thinking gave rise to a family of theories known collectively as modified gravity theories. These models attempt to explain the motion of stars in galaxies, the dynamics of galaxy clusters, and the shape of the universe without invoking dark matter. They propose instead that the law of gravity, as described by Newton and expanded by Einstein, might need to be adjusted, especially at large distances or very low accelerations. One of the earliest and most studied of these ideas is MOND, modified Newtonian dynamics. Proposed in the early 1980s by physicist Mordechai Milgrom, MOND suggests that Newton's law of gravity works well under normal conditions, but breaks down at extremely low accelerations, like those experienced by stars in the outskirts of galaxies. According to MOND, gravity becomes stronger than expected in these weak fields, which could explain why stars in spiral galaxies move faster than expected without requiring any extra mass. At first glance, MOND appears almost too simple. It introduces just one new parameter, a threshold acceleration, and with that adjustment, it can explain the flat rotation curves of galaxies remarkably well. In fact, MOND often predicts the rotation curves of individual galaxies more accurately than dark matter models do, especially in low surface brightness galaxies where dark matter is thought to dominate. This success has intrigued many researchers and kept MOND and similar theories alive, even in the face of mainstream skepticism. But Mondi has limitations, serious ones. First, MOND was not originally developed within a relativistic framework, meaning it didn't naturally align with Einstein's theory of general relativity. This made it hard to apply to cosmological models and observations like gravitational lensing and the early universe's evolution. Later developments, like TVS, tensor vector scalar gravity, attempted to fix this by embedding MOND in a relativistic theory, but these models introduced their own complexities and issues. Second, and perhaps more problematic, MOND struggles to explain the gravitational behaviour of galaxy clusters. In these larger systems, even with MOND's modifications, there still appears to be missing mass that MOND alone cannot account for. In some cases, theorists have had to reintroduce dark matter-like components to make the equations work, undermining the very purpose of a modified gravity approach. And then there is the bullet cluster. This famous system, formed by the collision of two galaxy clusters, presents one of the strongest pieces of evidence in favour of actual dark matter. In the bullet cluster, the hot gas from both clusters has collided and slowed down, as expected. But gravitational lensing maps show that most of the mass did not stay with the gas. It moved with the galaxies, suggesting a non-interacting form of matter that passed through the collision. MOND and other modified gravity theories struggle to explain this configuration without invoking some form of dark matter. So while modified gravity offers elegant solutions in some areas, it falters in others. Still, it serves an essential purpose. It reminds us that science must never be satisfied with a single explanation, even a popular one. It pushes researchers to think differently, to explore all possibilities, and to keep testing the foundations of what we believe. Beyond MOND, other ideas have emerged. Some involve adding extra dimensions to our universe, tiny curled up dimensions beyond the familiar 3 of space and 1 of time. In these models, gravity might leak into these dimensions, weakening its apparent strength and mimicking the effects attributed to dark matter, string theory, brain world scenarios, and other high-dimensional models attempt to fold dark matter into the geometry of space itself. Others suggest that what we perceive as dark matter might be the result of emergent gravity. The idea that gravity is not a fundamental force, but a side effect of deeper quantum processes involving entropy and information. These ideas are still in their infancy and remain speculative, but they hint at the tantalizing possibility that dark matter is not a substance to be found, but a clue to a deeper layer of physics yet to be understood. Still, the overwhelming majority of physicists continue to search for particle-based explanations, largely because they remain the most consistent with a wide range of data, from the cosmic microwave background and large-scale structure formation to gravitational lensing and galaxy dynamics. But there is wisdom in the minority view. If decades pass without a confirmed detection of dark matter particles, if all the underground detectors remain silent, and the particle accelerators yield nothing, then the scientific community may have to return, more seriously, to the drawing board. It may have to admit that the ghost in the machine is not a new kind of particle, but a new understanding of how nature works. It would not be the first time in history. There was a time when astronomers believed in a planet called Vulcan, which supposedly orbited between Mercury and the Sun. Its purpose? To explain the strange precession of Mercury's orbit. Observers searched for Vulcan for decades, even claiming to spot it. But Vulcan was never real. The problem wasn't with missing matter, it was with the theory of gravity itself. It wasn't until Einstein proposed general relativity that Mercury's motion finally made sense. Vulcan vanished, and a new age of physics began. Perhaps dark matter is today's Vulcan. Or perhaps it is real, hiding just beyond the reach of our instruments. Either way, we're on the threshold of something enormous. Either the discovery of a new class of particles that make up most of the universe, or a radical transformation in our understanding of space, time, and gravity. Both paths lead to wonder. And so, even as we build our detectors and point our telescopes, we must remain open to the quiet possibility that we are being told not just that something is out there, but that something is wrong in here, in the way we've drawn the cosmic map, in the way we've measured the stars, and in the way we've written the laws that govern the dance of galaxies. The universe is not obligated to reveal itself easily, but it does reward those who are willing to listen, not just to what is loud and clear, but to what is missing. In the vast, unfolding story of the cosmos, the earliest chapters hold some of the most important clues to the nature of dark matter. To understand how this mysterious substance shaped the universe, we must travel back nearly 14 billion years. Back to the time when the universe was a mere infant. A hot, dense soup of particles and radiation known as the primordial plasma. In those first moments after the Big Bang, the universe was a turbulent, energetic place. Protons, neutrons, electrons, photons, and a host of other particles collided and interacted at incredible speeds. The universe was expanding and cooling, but its contents were still tightly coupled in a chaotic dance. In this dense environment, dark matter played a crucial but silent role. Unlike ordinary matter, which interacted strongly with radiation and formed atoms only hundreds of thousands of years later, dark matter did not interact with light at all. It began to clump and cluster much earlier, responding only to the pull of gravity. These early concentrations of dark matter acted as the seeds of structure in the universe. Thanks to precise measurements of the cosmic microwave background radiation, CMB, the afterglow of the Big Bang, we can observe the imprint of these early fluctuations. The CMB shows tiny temperature differences across the sky, reflecting regions of slightly higher and lower density. These ripples trace the earlier stages of matter clumping under gravity's pull. Dark matter's presence allowed these small ripples to grow, pulling ordinary matter inward once it decoupled from radiation. Without the gravitational scaffolding of dark matter, ordinary matter would have remained too dispersed and energetic to form stars, galaxies, and clusters on the timescale we observe. Simulations of the early universe, incorporating dark matter, beautifully recreate the large-scale cosmic structures we see today. A cosmic web of filaments, sheets, and voids stretching across billions of light years. Dark matter forms the backbone of this web, with ordinary matter filling in the details. As the universe cooled and expanded, dark matter halos became the gravitational wells into which gas fell, triggering star formation and galaxy growth. The invisible web not only shaped the universe's skeleton, but guided its evolution. This early universe portrait underscores that dark matter, was not a latecomer or a minor player. It was present from the beginning, silently guiding the cosmic symphony. As we move forward in time, from the young universe to the mature cosmos, we see dark matter's handiwork writ large. Galaxies, clusters, superclusters are all embedded in vast halos of dark matter, invisible yet essential. The cosmic web is not merely a poetic term, but a literal description of the universe's architecture. Dark matter forms dense filaments connecting galaxy clusters like threads in a vast celestial tapestry. Between these filaments lie enormous voids, regions of near emptiness that highlight the contrast of matter's distribution. This large-scale structure is visible not in light, but in gravity's pull, in the way galaxies cluster and move. Surveys mapping millions of galaxies reveal this cosmic web, confirming predictions made by dark matter models. Dark matter's gravitational influence shapes the environment where galaxies live. Dense regions formed by dark matter attract more galaxies, fueling their growth and interactions. Less dense areas remain sparse, with few stars or galaxies. The cosmic web is a dynamic, evolving structure, growing from tiny fluctuations in the early universe to the complex pattern we observe today. It is the invisible frame that supports all visible cosmic structures. But dark matter's role is not only structural, it is also mysterious. Despite its profound influence, dark matter interacts only weakly, if at all, with itself or ordinary matter aside from gravity. It is a silent architect, shaping the universe but remaining hidden. This leads us to an even deeper question. What if our understanding of good and evil, of light and dark, of order and chaos, is incomplete? The universe is not a simple place of visible matter shining brightly against a dark void. Instead, it is a complex interplay of seen and unseen, known and unknown, light and shadow. The very term dark matter reminds us of this duality. It is matter that does not shine, matter that does not reflect light, but matter that holds everything together. In a way, it symbolizes the mysteries that lie beneath the surface of reality, forces and substances that influence us even though we cannot see them. As we contemplate this, we realize that dark matter is more than a scientific puzzle. It is a metaphor for the hidden forces that shape our lives, the unseen influences that guide the stars and our destinies alike. The cosmic web, born from the dark, invites us to explore not only the universe, but the boundaries of knowledge itself. It challenges us to accept that the universe is far more complex than our senses reveal, and that truth often lies beyond the visible. In the end, dark matter teaches us humility and wonder. It reminds us that while we have illuminated much of the cosmos, vast realms remain cloaked in shadow. And it beckons us forward, into the dark, into the unknown, into the beautiful mystery that is the universe itself.